Hi everyone, and thank you for being here listening to my talk. I'm Emanuele and I work for Compass as a security analyst, and I'm going to talk about how some of my colleagues and mine were able to pawn the Synology BC500 camera for the Pwning contest of 2023. But first, let's start from the beginning, shall we? Some time ago, we were at a conference like you are right now, and we were watching a talk called Whatever Pwning, where basically two guys were showing how they were able to pawn a router from the one interface. And after the conference, we discussed internally and decided that we wanted to participate to the next Pwning edition. Or at least we wanted to try, since it was our first time. And we didn't know what to expect. After some discussion internally, we created a team composed by 5 people. It was composed by me, Yves, Urs, Cyril, and Lukasz. If you're asking yourself why there are some avatars or why I chose some avatars, that's because internally we have a policy that everyone has its own avatar. So if you want to use them for phishing purposes, just use them. I don't know how many of you are familiar with the Pwning competition or knows how it works. Actually, I'm just going to give you a little bit of introduction on the Pwning competition, so we are on the same page. There are some rules, and these rules are quite simple. You have 3 attempts, and for each attempt you have like 10 minutes time span where you can perform your exploit and achieve remote code execution. If you fail all the 3 attempts, or if your exploits take longer than 10 minutes, it's considered a fail. And if you fail all 3 attempts, you fail the competition. Then your exploit shouldn't require any interaction. I mean, you are allowed to just type the command to start your exploit, but apart from that, you are not allowed to, for example, reboot your target or unplug it and plug it to the network again. You can just sit and wait until your exploit is done. Then everything is unauthenticated, meaning that you have to simulate an anonymous attacker, and the targets are fully set up, so any default password is just changed, so you don't know the password. And in the end, all the targets are fully updated to the latest available firmware from the vendor website at the time of the competition, meaning that if 1 day or 2 days before the competition there is a new update that fixes your exploit or the bug that you have exploited, you're screwed. Then there are different categories. You have like the camera categories, you have the speaker category, the printer category, and as you can see from the image, each category has its own bounty. Considering that it was our first attempt at the Pwning, we decided to select the easy ones, like the security camera and the printer categories. And because there are several targets from different companies for each category, we specifically selected the Synology BC500, of course, and the Lexmark printer. So we bought them, and the target arrived. The first one that arrived was the Synology camera, so we just opened it and connected to the available interfaces. Few days later, the printer also arrived, but as you can see from the image, the printer was broken, and we couldn't really start analyzing it. So we just asked for a replacement, but it takes few days, so that's why we started first with the camera. Now let's see how we got root access to the camera. We open, of course, the camera, and we notice these 4 pins. After some testing, we realized that it was the UART port, and we attached the USB to serial adapter and connected to the laptop. After that, we rebooted the camera, and we noticed that we, of course, correctly set up all the configuration for the UART, like the baud rate, the data bits, and so on. And we got the output of the U-boot loader. So after some information related to the boot procedure, something appears that looked like a shell login. We tried to find default credentials online. We tried to use tried to guess the credentials, but nothing worked. But luckily for us, the Synology published all the firmware updates. So we could just download the firmware updates. That's what we did. And once you download the firmware, it's like a bin file, which is composed by different parts. The first one is the header, which contains like information related to the update, like the version of the update and other, how many partitions are inside and so on. Then you have an array of partitions, and each partition has the name of the partition and the image, and one of which was the rootfs, and as you may guess from the name, contains the root file system of the camera. And there was also the signature for tampering verification, for preventing any tampering verification. After we extracted the file system of the camera, we, of course, checked the passwd file, and we noticed that there are two users that were allowed to log in, or at least that has a shell. The first one is the root user, but as you can guess from the exclamation mark in front of it, the root user is blocked, so it cannot be used to log in into the camera. There is also another Synodebug user with a password set. We didn't really know what this password was. We tried to crack it, but we weren't successful. So we started analyzing and performing some reversing to understand how this password was set, or when it was used. After some reversing, we discovered that the password of the Synodebug user is updated whenever we change the password of the user on the UI interface, using the same password. So it means that if you change the web user password, the same password is set for this Synodebug user. We tried what we discovered, and actually it worked. So we had root access to the camera using the UART connection. And then let's see what are the services exposed on the camera, because now we have root access on the camera, we can debug, see the logs and so on, but we still have to find all the services that are exposed. We simply ran nmap, and we discovered, nmap discovered these 4 services. The 80 and 443 are just the services that exposes the web UI, where you can configure the camera, change the configuration, see the streaming of the video streaming, and so on. You have the RSTP protocol, RTSP protocol, and also there was another port, the 49152, which wasn't recognized by nmap. But after some reversing and testing, we identified it as UPnP. Now, as you recall from the slide before, we had root access. So we also ran nmap to see if there was any service listening that wasn't listed by nmap or wasn't identified by nmap. And in this case, we found a UDP server on port 19998. And we analyzed it, but we realized that this one is just an initialization service, and it's used when the camera is not initialized to just initialize the camera. And whenever the camera is initialized, this service is still listening, but it rejects any packets. So in our case, because the targets will be like full configured, it's useless. Then, during the analysis of the Synodebug user, we identified the function that was responsible for changing the password whenever the password of the web user is changed. And as you can see from the image, it seems that some of the parameters are used to create a command that will be executed by system. That's actually great because we noticed that one of the parameters was the password that you enter when you do the change password functionality on the web interface. We tried one of the easiest payload you can find for the command execution, just to try to create a file 123 on the TMP directory, and surprisingly it worked. So we had an authenticated password change, let's say authenticated command injection. The problem is that as the name implies, is authenticated, and we need an anonymous one, but we have something. Then we looked at all the available software that could interact with the camera, and one of them is the surveillance station, which is actually a tool developed by Synology that allows you to manage multiple cameras in one place. So basically you can configure the cameras and you can see all the streaming in one place, and you can also change configuration and so on. And luckily for us, it also supports our camera, the BC500. So we downloaded the tool, we configure it to connect to our camera, and we analyze the configuration. We sniff the traffic and analyze the communication. It turned out that it uses HTTP, the HTTP protocol to communicate with the camera, but actually the plain text HTTP, not the HTTPS. So we could read the request and the response. And as you can see from the image, it also uses HTTP basic, which means that you have access to the password that was entered. And exactly, you can just decode the base64 information, and then you get username and password that you can use to authenticate to the web interface. So putting all together, we can turn the authenticated command injection into a non-authenticated command injection, because, for example, let's suppose that you have a network where you have the surveillance station connected to the camera. You are an attacker on the same network, and you can sniff all the packets that are sent to the camera, and at some point you can just grab the password from one of these packets and use it to log into the web interface, and then perform the password change by injecting all the commands that you want. So now we have an anonymous remote command injection, but to be honest, it was our first pwn attempt, and we didn't know whether we could ask for this specific setup or not. We decided to identify another weakness that would be exploitable without any specific setup and with the default configuration of the camera. Then we started looking at all the exposed services, and one of the first thing we did was to see what are the APIs that can be called as an anonymous user. As everyone would do, we just from reversing, we just retrieve all the APIs that we could find. We throw it into burp intruder and see without any session and see which one will answer with something different than 401. And as you can see, the first 10 APIs allows unauthenticated access. But then we were wondering, what about other methods? Because GET are used to just retrieve information. We would like to see if there is an API that allows you to modify something. So we tried the same with the put request, the put method, the post, and so on. And we identified these 5 APIs that return a different status code from 401. We analyzed it more, and we realized that the activate API only accepts the string true. If you try to send whatever other string, it will return an error. Then we checked the language API, which seems to accept any string. And the remaining 3 APIs were always returning an error. And after some reversing, we identified why. That's because they were trying to modify some files inside a read-only file system. So we focused on the language API, which seems to be the most promising one. And this is the standard request. As you can see, you have on line 7 the JSON string. But if you look at the line 4, the content type is set to application JSON. So we just tried to send a request including a JSON object, and of course we got an error back. But if you look closely to the response, you will see that only the JSON key is returned and not the full response. So it means that somehow there is like a parsing involved, even though it's not supposed to receive any JSON object. So we continue playing with it, and we found some particular behaviors, like, for example, if you send a JSON object containing 52-character JSON key, it will just return a 500 error. But if you send another JSON with a 48-character JSON key, it will return another kind of error, but if you look at the response, you will see additional hex bytes that are also returned. And these bytes are not present in the HTTP request. So it means that some sort of memory leakage was present. And now let's talk about the analysis of this weird behavior. But first, we have to analyze the HTTP flow to understand what are the main components involved. So you have the UI, and whenever the UI sends the HTTP request to the WebD daemon, the WebD daemon will just forward this request to different CGIs based on the API that you are calling. In our case, it forwarded the call to the Sino Camparam CGI. And in order to pass all the information, it will just take the headers and passes them as environment variables. And if you're sending a post request, the body will just send a standard input to the CGI, and then the CGI can process everything. This is how the architecture looks, and it will be important for later, also for the exploit. With that being said, we attach GDB to the Sinocam param CGI to understand what's going on. And when we were sending this weird JSON object, and what we see is that it's like this really nice backtrace where you can see that actually the error is not on the Sinocam param CGI itself, but in a dependency called libJSON, which is an external library used to parse JSON data. So after some reversing, we found the code where that triggers this exception. And as you can see here, there is the scanf, which is used to parse the JSON object and the JSON key in order to see whether there is a space in it, and it will just store the two different data in two different buffers. Luckily for us, there is no length check, or they forgot to add any length check, and the buffer are fixed on 32 and 12 characters each. But actually we can send how many data we want. So here we got like really excited also because we checked the GitHub code of the libJSON library, because the libJSON library has a GitHub repository where you can just browse the entire code. We looked for all the different versions, and we weren't able to find anyone who has this scanf call. So this means that developers added it for some reasons, but I don't know, to be honest, why, but yeah, great for us. But before exploiting this, we have to check what are the mitigations in place. So we ran checksec, and we found that there is no stack canaries, and that's great. However, the stack is not executable. So this will be the first issue that we have to solve when we are writing the exploit. Then there is another thing. Then the randomization is enabled. It means that we have to deal with ASLR, but that's another issue we have to solve later. And there is one more thing. If you read the library documentation, you will see that it only accepts valid UTF-8 characters. That's actually not really great because UTF-8 is a pain. It encodes different characters with bytes that goes from 1 to 4. If you can have like 1 byte characters, and you can use from 0 to 7F, and it's like your normal ASCII range, but it's not so great because like a lot of your payload characters are missing there. But luckily you can use 2, 3, and 4 bytes. You still have some limitations, but on certain bits, but at least allows you some flexibility when you are writing your payload. But for the moment, we have to just add the UTF-8 as another issue that we have to solve. After having identified all the issues, let's try to solve them and write our final exploit. So the first issue was the stack that was not executable. So it means that we cannot use something called the easy approach, where basically you put the shellcode in the stack, you have the return address, you overflow the return address pointing to the beginning of your shellcode, and the shellcode gets executed. But in this case, it doesn't work because the NX bit was set, so the stack is not really executable. But we have plenty of solutions, like, for example, you can use the ROP gadgets, meaning that inside the padding and the commands that you would like to execute, you can just include also addresses of gadgets that will be executed like in a chain and will, let's say, fix the registries and other information in order to allow you to execute the command that you want to execute. Then we still have the return address, and you can just overwrite it pointing to the first gadget of this ROP, and then after some magic, actually your command will be executed as system. And we can consider then the NX fixed as NX issue as fixed. But during the development, we realized that actually we don't really need any ROP gadget, because while we were overflowing the stack, we were also overflowing some pointer address of a function that is used later in the code in specific conditions, and our payload was already passed as input. So we realized that we can simply change the address of this function pointing to the system function and just wait until the code calls this function pointer. And because of this setup, we don't need to deal with any additional address, and we can just remove them. And we have like a simple padding plus command plus the address that we want to use. Then we have ASLR. And we looked at the camera and asked ourselves, how random is it? Because, yeah, it's not a modern system, so it means that it shouldn't have quite a lot of ASLR. It's still an IoT device, so it doesn't have so much power. And we looked at it and we saw that the ASLR was only set for 8-bit. That means that if you have like an address like this, 1, 2, 3, 4, 5, 6, 7, 8, only 4 and 5 will be random for each invocation. Which means that 8 bits are random, so in total there are like 256 possibilities. So it's not easy, but could be. But the main question we had now is, shall we try brute forcing that address, or should we try to find another vulnerability that would leak an address? So we kind of analyzed that and had a look at it. And the interesting part is that when you are sending the payload, that one will be forwarded, that will reach the WebD process, and the WebD process will forward your payload to the Synology CGI. And if you guess the wrong address, it will crash. And you can do, and we analyzed that basically it happens the same every time you enter you send a new payload. But you can continue doing that and observe that it doesn't really crash the WebD daemon, which is the web server. It crashes an additional thread. So that's great for us because it's really fast. Because if we would have crashed the web server, we have to wait until the web server will just restart again. But with only crashing the Synology thread, we can just send as many requests as we can, and the WebD daemon will always answer. So, here. And so, with having observed that, we just used the brute forcing approach, and we just didn't want to check for any other vulnerabilities that would leak an address, and we tried with this. And we are trying now to solve also the UTF-8 problem at the same time, and hopefully I can try to tell you how we did that. So if you want to encode an address like this one, like 768XYB34, where X and Y are just random bytes. This one can be random due to ASLR. The idea is to just choose them to be something that is a valid UTF-8 character, and basically pass the UTF-8 validation of the camera. Once this is passed, it will hopefully reach the vulnerable function, and we hope for the best. If the address is not correct, then it will crash, but then we can send the same address again in another request. It will pass the UTF-8 validation, and it will crash, and we can continue doing that and doing that and doing that until at some point the ASLR will just set up the program in a such way that it will align with the address that we have sent, and we could get code execution. And now the next question would be, can we find an address that will pass the UTF-8 validation? As you can see, the 7.6 is fine, the 3.4 is fine, because they are lower than 7F, but we have an issue with the YB, because actually it's a little endian, as you can see on the second column. B is already up to 7F, and then it doesn't work, so we have to find a valid address that will pass this validation, and also we have to find like a valid address for a valid function that we can call. And of course, we decided to use system, and we hard-coded 3 and D. And why? Because it can be encoded with this UTF-8 payload. Now the question is, okay, we have an address, we can do brute forcing, but is this feasible? Because for the Pwning competition, if you recall the rules, you have like 10 minutes. So we have to identify how much time it takes to just find a valid address. And we did some math and discovered that we should get around 98 possibility of at least one success after sending 1,000 requests, and more than 99% after more or less 1,200 requests. Next question is how long it takes for the camera to process one single request, because it's not like a super scale web server, but it's like a small IoT camera. After some tests, we identified more or less an average of 100 milliseconds per request. And in theory, we should be able to send 6,000 requests in 10 minutes. So we can mark both issues as fixed. And now this brings us to our, let's say, final payload, where you have like this padding to reach the overflow. And then you have inside the padding, two additional commands. One is to enable the root user, and the second one is to enable telnet access. Then you have some additional padding, and at last you have the address of the system function. And if you recall from the previous slide, the root user was blocked, but you may ask yourself, how can you access the camera using the root user if you are not changing the password? It turns out that we cracked the password, and it's set to 12345 for all the cameras. So once you have unlocked the root user, you can log in using these credentials via SSH or Telnet. So we started testing our exploit in a real scenario, and we found that the reality is a little bit different than the theory. Usually when everything is working, you have more or less 100 milliseconds as response time. But sometimes there could be addresses that will point to, for example, a loop, an infinite loop, or to a function that waits for some input that will never be inputted. And if that's happened, some of the threads will just hang. And if you have more threads hanging, as you can see, the response time will slow down. And that's actually a problem. And because it can slow down the exploit, and then we could fail the 10 minutes time. So we have to find a solution, and one of the solutions is reboot. During the testing, when we were testing the JSON payloads before, we found this weird behavior. If you send like a JSON object with a JSON key with exactly 185 characters, the WebD process hangs. That's a small difference, but that's a key for the reboot, because it's not the Sinocamparam process waiting, but it's the WebD process waiting. And why it's important? Because we noticed that there is a watchdog process on the camera that checks how many WebD processes are unresponsive. And if more than 10 are used, it will just kill the WebD camera and reboot the camera. So with everything we have said, we have the final logic of the exploit, which means that at the beginning it tries to find the correct address, and let's say that we got an error. It's not the correct one, but the exploit detects that there is like a slowdown on answering the request. So it starts what's called the reboot procedure, or what we call reboot procedure, which means that it starts sending multiple times the request I just showed you, and until it detects a reboot of the camera, and after it detects a reboot of the camera, it goes back to the exploiting phase and checks how long it takes, and yeah, it continues until it finds the correct address. Now everything was ready for the contest. So we booked the flights for Toronto, and we decided that 2 of us were going on site and the other 3 would remain in Zurich. So during the flight, we decided that Siri and Eve goes to Toronto, and during their flight, we found that Synology released a new update shortly before the competition, and we started panicking. So the one that were in Zurich installed the new firmware and tested the exploit, but luckily for us, it was still working. However, the vulnerability of the change password that I told you before, the authenticated remote code execution on the change password, was fixed, with other additional vulnerability fixed. Here I prepared a small video showing you how the exploit works. As you can see on the left, the script runs and it tries its best to find the right offset. It will take a few seconds and it should be pretty quick, of course, because I made a video out of it. And after a few seconds, you should see the payload triggers and you observe on the right the standard web interface of the camera. And at that moment, once you refresh the page, you will see the Compass logo, meaning that we were able to replace the web server of the camera with our own. So in the end, we still managed to pawn the camera. And here is the proof of the zero-day initiative, that tweeting that we were able to successfully use our Stack Overflow attack against the Synology BC500. But if you look closely, they wrote something like previously known. But actually, what does that mean? Because it's supposed to be like 0 days, so it doesn't make sense. Actually, I forgot to tell you that there could be several different teams trying to pawn the same device. And what the pawn-to-own organization does is creating a drawing and decide with the order of each team. And for example, in our case, we were drawn as third, meaning that we had to wait until the others to complete their attempts. The first team was successful, and they exploited the camera, and they got the full bounty. Then the second team exploited the camera and they got a fraction of the bounty, just because the bounty I showed you at the beginning of the slides are for the first team pawning it. Then you have like a fraction of the bounty. And then it was our turn and we were successful, but we got like still a little fraction. That's because we used an exploit that one of the other team used, or maybe both of the team used, and that's why they've written like collision previously known, meaning that some of the groups before us used the same exploit. So after this positive experience, we had trying this year at the Pwning 2024. This time it was not in Toronto, but they moved to Ireland, in Cork, and it was on October from 22nd to 25th. And as you can guess from this tweet, we were able to successfully exploit the Ubiquiti AI bullet camera. I cannot tell you more detail about that because we have to wait until they provide a fix, but in the coming months we will write some blog posts, so you can check the Compass website if you want to know more once we are allowed to talk about it. And because of time and this presentation, I cut some details that maybe you would be interested in. So if you are interested in, here we have like the blog series with all the different articles explaining in much more details everything I just showed you here. Or if you want to know more. And that's the end of my presentation.
Thanks a lot, Emanuele. Amazing talk. Thanks a lot. Really. I guess we have time, so if there are any questions in the room.
Hi, a very nice talk. I have a quick question about the vulnerability you found with the scanf. That was in the JSON library, right? In the Anson.
Yeah.
Do you have any idea what they changed this? Because this like almost smells like a backdoor. Like, why would they even touch this?
No, actually, I don't know what they wanted to do, because when we saw that scanf, we thought that maybe they have some JSON keys containing spaces, so we looked at different configurations, but we weren't able to find any JSON containing spaces, nothing. So I guess probably it's something they modified before, they forgot to just remove that once it was not required anymore.
Anyone else here? please, someone can bring a mic. Here in the middle, Jean-François. So meanwhile, I just remember that we have a change in the schedule and the RUMP session will start at 4:30 after the last talk.
Hello, thanks for the presentation. I'm curious to know how long did it take for Synology to patch the exploit from when you revealed it during the Pwning to like when the firmware release was released?
Well, to be honest, I don't recall. I recall that we could write the blog post like 3 months later. But I guess they should be pretty quick, but I don't remember, to be honest, how much time.
Okay, thank you.
There was someone with another question. I don't remember. Here, thank you.
Thank you for your talk. I have a question. How you managed to identify the file structure of the firmware binary once you recover it from the Synology website?
Sorry, can you repeat?
How you identify the file structure of the firmware binary?
In that case, we first read some articles regarding someone else before that was able to just show you how it was composed. That's more or less. And then there were some differences, but we just, starting from there, we had like a good start, and then we just modify something, and yeah.
Sorry, it's probably a very noob question, but if I understand correctly, you just try an address, so with a randomized number, and the system, every time you call it, creates its own random number, and you just hope for a match, if I understand that correctly.
Yeah.
At one moment you said that you also thought whether you should try to find out what the current random number is, as to make your attack go faster. But then how would that work? If you make a first request, you get the randomized address, and then you make the second request, that would be a different random address, or how would that work in that case?
Well, actually, it should be that you can, using one single request, you can leak the address and then somehow check and modify all the addresses in order to just find the correct address. Probably it shouldn't actually work. Or it should be. I have to think about that, to be honest.
So it was a new question, sorry.
With the ASLR, usually you have to find a vulnerability that leaks some addresses, and then starting from there, you know more or less where to put all the other pointers. I didn't think much about that because we started thinking with the brute forcing, and then we go with that. Once we found that the ASLR was just 8 bits.
Thanks.
Any other question? Seems so. Thank you again.